Hello, and in this video, I want to go through um, something I found online about the coefficient of thrust for a propeller. So, in previous videos that I did, I spoke about the benefit of the advance ratio for a propeller. So, if this is the advance ratio here on the x-axis, we can see um, to keep the efficiency of the propeller reasonably high, we need to change the blade angle at different speeds. And that makes sense when you're using a constant speed propeller, which changes the blade angle. And on that previous video, I spoke about this angle of advance here. And we said that the angle of advance, or the tan of the angle of advance, was equal to the aircraft velocity times the propeller velocity, the rotational velocity of the propeller. And uh, if we look at this omega r, well, omega is the rotational velocity in radians per second, and that's RPM divided by 60 multiplied by 2 pi. So that just becomes radians per second by 2 pi. So if I go omega r, it's n 2 pi by r, and 2r is d. So I get nd pi. So I can put in here nd pi. And you can see that that's very similar here to this advance ratio. So the advance ratio is provided as the velocity over nd. And there is an equation then that says that the efficiency of the propeller is 1 over 2 pi, the coefficient of thrust over the coefficient of torque times j. So there's the j and the 1 over pi. So j and 1 over pi here. And I was interested on this part of the expression, this coefficient of thrust and coefficient of torque. And I was looking online and I came across this reference from MIT, and they actually go through the coefficient of thrust and the coefficient of torque. And what I thought it might be beneficial is if I made a video on that. So I'm basically just taking their notes and explaining it. Okay, so what they said was, let's assume that the thrust is a function of the propeller diameter, the rotational velocity, okay, so the revs per second, the density of the air, the viscosity of the air, the bulk modulus of the air, and the flight velocity v. And then they just said, okay, well, let's say thrust is some constant times d to power of a, n to the power of b, rho to the power of c, nu to the power of d, k to the power of e, and v to the power of f. So and I've explained up what all of these are over here on the right hand side. So what they were going to do then was use dimensional analysis. So the thrust, well, thrust is just a force, and force is mass by acceleration. So basically saying mass by acceleration is into this constant times on all these factors here. Now acceleration is defined as the rate of change of velocity or change of distance with time squared. Meters per second squared. Okay, that's the units of it, meters per second squared. So my expression here, mass by acceleration, is really mass times distance over time squared, meters per second squared. And if we use these letters to symbolize mass, distance or length, and time, MLT, we can change this expression. So we can say that m is mass. Okay, so there's the mass. The distance s, well, that's a length, so that's L. And the time t, we're going to use the capital letter T. So that's t squared, but it's t to the minus 2, okay, because it's per second squared. So mLT to the power minus 2. And that's equal to this constant, whatever that is, times all of these factors to these different indices. All right, so then the MIT slide went on to 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 turn this into some dimensional analysis as well. So d to the power of a, well, d is a distance, so it's just the length, so that's length to the power of a. The revs per second, well, it's per second, so that's time to the power of minus b. Okay, so because it's 1 over t. Density is kilograms per meter cubed, so kilograms is mass, meter cubed is meters is distance, so per meter cubed is distance to the power of minus 3, and that's all to the power of c. And then the viscosity nu. Viscosity is what is it measured in? Is meters squared per second. So meters squared, so that's length squared per second. So d to the minus 1, t to the minus 1, sorry, all to the power of d. And the bulk modulus was newtons per meter squared. So I've done that down here. Newtons per meter squared. Well, newtons is mass by acceleration. Meter squared is just length squared. Acceleration is distance per second squared, so that's distance L, length per second squared, t squared. The L will cancel, so I get m, L to the minus 1 and t to the minus 2. So the bulk modulus is m, L to the minus 1, t to the minus 2, e, because we're to the power of e here. And finally, the flight velocity v, well, that's just distance per second. So it's L for length per second, so t to the minus 1. Okay, and that's all to the power of f. Okay, so there's our force, our thrust, and it's equal to k times L to the power of a, t to the minus b, ml minus 3c, L squared t to the minus 1, all to the power of d, ml to the minus 1, t to the minus 2, all to the power of e, and L t to the minus 1, all to the power of f. Okay, so that's my thrust. So my thrust is equal to this equation when I'm using dimensional analysis. So let's compare the indices. So over here I have m to the power of 1. There's m. I have m to the power of c. There's mc. M to the power of e, me. And just from the power of indices, m to the power of c by m to the power of e is equal to m to the power of c plus e. So this is really m to the power of 1. Divide across by m, I get 1 is equal to c plus e. And I'll do the same then for L. So if I compare the L indices, here we got L to the power of 1, so there's L. We got L to the power of A, L to the power of minus 3c, L to the power of 2d, L to the power of minus e, and L to the power of f. Okay, again, I'm going to add the indices. So if I multiply these, it's the same as adding the indices. So I have L to the power of A minus 3C plus 2D minus E plus F. And if we divide across by L, so L goes into there once. Sorry, if I just, that's wrong to say. If I just compare the indices, so L to the power of 1. So 1 is equal to A minus 3C plus 2D minus E plus F. And finally, we'll do it for T. So over here we have T to the minus 2. And that's equal to t to the minus b minus, t to the power minus d, t to the power minus 2e, and t to the power minus 1f. So t to the power minus 2 is the same as t to the power minus b minus d minus 2ef. It's just comparing the indices then, so minus 2 is equal to minus b minus d minus 2e minus f, and if I multiply by minus 1, I get 2 is equal to b plus d plus 2e plus f. Okay. So that was my expression from the m coefficients, and I've just rearranged that to get a value for c. And this was my expression for the L coefficients, and I've just rearranged that to get a value for A. Okay, and this was my expression for the T coefficients, and I've just rearranged that to get a value for B. And I'm going to substitute these back in here for A, B, and C. Okay, so when we do that, we get L to the, we get d to the power of A now becomes d to the power of, well, A was 4 minus 2e minus d minus f. N to the power of B is now n to the power of 2 minus d minus 2e minus f. Rho was C, and C is equal to 1 minus E. So that becomes rho to the power of 1 minus E. And we still have nu to the power of d, k to the power of v, and v to the f. Okay, so we have d to the power of 4, so I'm going to take that out. There's d to the power of 4. We've n squared. We're going to take that outside. And we have rho to the 1, so we're going to take that out. So if we look at the coefficients then with d, okay, so we had nu to the power of d, and then we had the diameter here to minus 2d, so that's minus 2d, and we'd n here to the power of minus d, so that's just n to the power of d. So grouping, the powers to d, that's what I get. For k then, we've k to the power of e, and we have d to the power of minus 2e, so d to the minus 2e, n to the minus 2e, so that's n squared e, and rho to the minus e, that's rho to the minus e here. And finally, to the power of f, we had v to the f, and then we had d to the minus f, so there's d to the minus f, and there's n to the minus f. Okay, so now so don't forget, this is our thrust is equal to these values here, and then some function of these factors. Okay, so if I look at this part of it first, so nu over d squared n. So that relates to the Reynolds number. So if I look at Reynolds number is the velocity v times the characteristic length L over the viscosity. And so normally you would say, if this was an airfoil, so this is the air going over it. So that's the velocity, and this is the characteristic length L, which is normally the chord length. Okay. So that's what the Reynolds number is. So if I invert that, then 1 over RE becomes nu over VL. And if I have a propeller blade, the air coming in is that way, and then this is the air due to rotational, and this is the airflow over the propeller. So it is proportional to this omega r. Okay, so the velocity is proportional to this omega r, and omega is just radians per second. So you would say um, omega is equal to 2 pi n, and then r. So 2r is d, so we got pi n d. So I could say the velocity here is proportional to nd, and the propeller, okay, so we said this length here is the characteristic length, but you know the propeller sort of tapers here. So the length is, you know, some taper ratio, the overall dimension d. So this becomes d. So what I'm saying is this is really proportional to nu all over n d times d, which is nu over n d squared, okay, which is what we have here. So this is really the 1 over the Reynolds number. It's proportional, or it's a function of 1 over the Reynolds number. If we look at the second part of it then, if I look at the Mach number, well, Mach number is the velocity over the speed of sound. So again, if this is my propeller blade, you know, it's the velocity over the blade divided by the speed of sound. So I've just explained that this velocity is proportional to omega r, which is effectively proportional to nd. I'll do capital D. That's the way it should be. And we'll keep that in mind. Okay, the speed of sound here is gamma RT, where gamma is the ratio specific heats of air, and it's a constant. It's 1.4, and this the R is the universal gas constant. So this is 1.4, and this is 287. That's joules per Kelvin. No, per kilogram. Joules per kilogram. And this is the temperature. Okay, now if I take the universal gas law, which is, you know, the density is equal to P over RT, and if I transpose that, I'll get T is equal to the pressure over the density times R. So I'm going to substitute that back in here. So now my Mach number is proportional to, well, omega R is basically, sorry, I'll start again. I want to get rid of the square root, so I'm going to square both sides. Okay, so the Mach number squared is equal to omega R squared, which is really proportional to n squared d squared. Saw that from here. And then we have, if we square this, we get gamma RT, and instead of T, then I'm going to put in P over rho R. And the R's will cancel. So we just get 1 over gamma, which is the same as multiplying 1 over rho, sorry, which is the same as multiplying by rho. So we get rho d squared n squared all over gamma, and this is a constant. So we could just say it is proportional to rho d squared n squared, which is what we have here. So I could say this is proportional to 1 over the Mach number squared, or 1 over Mach number squared. So it is proportional to the Mach number, okay? And eventually, finally, this value here, well, we opened up this this screencast looking at this, and this is called the advance ratio J. All right, so going to put all of that together, and we're going to say that the thrust is equal to some value rho n squared d squared, and it's a function of the Reynolds number, the tip number, and the advance ratio. And we can lump this and that into some coefficient, and we call that the coefficient of thrust. Okay, so now we're saying, and this was always the thrust here, this part of it here. So the thrust is some coefficient of thrust, rho n squared d to the power 4. And if I look at the torque, well, if I have a lift force from the airfoil, so that's the thrust, I'll have a drag force, and that's acting at a distance d to give us torque. So we'll call this coefficient of torque, rho n, and then we're just multiplying this by this value d, so we get d to the 5. So the torque is CQ rho n squared d to the power 5. All right, so we're nearly there now. This is a long video. So the power produced by the engine, power is torque times omega, and we've seen that omega is just 2 pi n. So that's the power delivered by the engine. That's the power in. The power out. So the propeller is delivering some power now, and that's equal to the thrust times the velocity. So, so that's a force by distance over time. Force by distance is work per second is power. So the power out then is thrust times velocity. So if I want to look at the efficiency, I want to get what do we get out from what do we put in. So what do we get out is thrust times velocity. So instead of thrust now, I'm going to say it's CT rho n squared d to the power 4 times the velocity, all over the torque, which is CQ rho n squared d to the power 5, 2 pi n for omega. And there's my formula again, and then things just start cancelling out. So that goes, that goes, that goes, that goes, that goes. That comes just d. So we get CT times V all over CQ d 2 pi n. Just separate those components out. So the 1 over 2 pi, that's that. CT over CQ is there, and then I get V left at V over V over ND. And we said this was equal to J. So the efficiency is equal to 1 over 2 pi CT CQ over J. And that's where we started from. So that's where that all comes from. And I'm very thankful for that website there on MIT. And I hope that's of some benefit to you all.